we've already got the test and demonstration sites that I mentioned. That is Hexagon, Blue Gem Wind, which is a joint operation between Simply Blue and Total Energy. Floventis, who are partnered with Serco. Offshore Wind Limited, who are a partnership of Cobra and Flotation. As I've mentioned, the leasing round is confidential, so we don't have official confirmation from the Crown Estate who's involved. However, we know that EDF, partnered with the ESB and Noventis, are bidding for one, or they've confirmed that they are. Equinor has confirmed that they're bidding, and RWE has confirmed that they're bidding. We're also fairly confident about these, at least some of these other developers will be bidding as well, because they've taken part in the network of developers for the Celtic Sea. So some of these probably are, or conglomerates of these are probably putting in bids as well. What's going in? Well, we can give some details here. For instance, Hexagon, we know, are using their own twin wind platform, and they're using Mingyang 8 megawatt turbines. Blue Gem for Erebus, we know, is using the Windfloat platform, as you can see there, which has already been used for the Windfloat Atlantic pilot test site off Portugal. However, most developers haven't confirmed their technology, with some caveats about levels of confirmation. And in many cases, they likely haven't even selected their platform or turbines, because the rate of development of these devices is very, very rapid, and people don't want to commit at this stage to something that they'll be deploying in 10 years' time. However, roughly we can say that the expected capacity will be turbines between 15 and 20 megawatts capacity, of a max height of around 300 meters with a hub height of 150 to 180, and a platform width of about 50 meters. And the example, the phrase that always springs to mind when given by RWE is that it's the equivalent of building an Eiffel Tower on top of a Prince Palace Stadium and floating out to sea once a week for 5 years, right? Beyond the turbines and the platforms, there's lots of other components that are needed. Obviously the port facilities, storage facilities, the vessels, the cables, the anchors, the substations. So it's not just a matter of the big metal bits. There's lots of string that goes between them, and there's lots of places to store them when you're getting ready to tow them out, right? How is it being supported? They're not going to be able to, it's not expected they'll be able to sell at market parity, so they will be supported through probably the Contract for Difference scheme. I'll have to wrap this up now, apologies. Hexagon has already secured CFD funding, Contract for Difference funding, in 2022. No one else has yet. However, we're expected to get more in the 2025 rounds. The 2025 rounds do include clean industry bonuses, which means that the people who are awarded CFD will need to show engagement with local supply chains and more sustainable manufacture. I've mentioned the port facilities are going to need to be improved, and that's had some support. That's not just in the UK, that's also in Ireland there. So we're looking at South Wales, obviously, because that's where we are. But there might also be ports in southwest England and ports in Ireland, which might be the basis for some of this work. And then we will return to the agenda because I've slightly overrun. Thank you very much.
Thank you. Okay. Thank you, Michael, for that overview. The one thing I hope you all learnt from that was these things are really big, and the ones in the pictures are about half the size of the ones we're going to be deployed in the Celtic Sea. So they're even bigger than the really big you've just seen. Okay, somebody who's helping develop something, which is real technology, Will, if you want to come up, Will. Will is working with our partners Marine Power Systems on a project. Some of the Marine Power Systems teams are in the room and online, so yeah, let's find out what they've been up to. Right, you need to wear that for the last.
Okay, right, hopefully that doesn't fall off. Yep, not very well. Okay, thanks, Ian. Okay, so what I'm going to talk about today is a current Innovate UK project. So this is a collaboration, well, it's led by Marine Power Systems. We've got a few people from Marine Power Systems here today, with multiple partners, including Swansea Uni. So we're taking one of the technologies, so one of the platforms that Michael just showed, and we're looking at optimizing that. There's a sort of list of contributors. We've got contributors from Swansea University and from Marine Power Systems. So I put this slide in. I'm not going to dwell on that because I think Michael's given us quite a nice outline as to the project background. But the main project we're looking at is, so there's going to be loads and loads of these floating platforms or deep water platforms out in the Celtic Sea. So how can that benefit Southwest Wales? So, as Ian said, these things are really big. So it's got a sort of tetragonal structure here. Some of these tubes, sort of 9 meters in diameter, so big structures. They currently have, into the thousands of tons of steel. So we need them to be able to be preferably made in the local area. So this project started with an initial design from Marine Power Systems. It's like a tetragonal shaped. It's got advantages over some semi-sub designs. Has a low mass per megawatt. Lots of similar parts, so it's sort of easy to manufacture. It's all steel, so it's recyclable. It's a towable structure, so it can be towed out easily, and it's fairly stable as well. Obviously, the more stable it is, the more steady your turbine is, the more efficient it will be. So the problem with these structures, they're really big, but a lot of the steel in there is really, really thick. So Tata, over in Port Talbot, can make steel sections up to about 20 mil. This has got sections way more than, maybe more than that, sort of 40 mil, 50 mil sections. So the idea of this project is, can we do some optimization of the design, reduce that section thickness down, make it so we can make the steel, or use the steel that we make in Southwest Wales, like over in Port Talbot. If we're going to thicker sections, we're taking steel from somewhere like IJmuiden. If you're taking it from IJmuiden over in Holland, you might as well just make the things there and ship them over here. We're not going to benefit Southwest Wales. This project, it's, like I said, it's a collaboration between Marine Power Systems and some partners. We've got Tata Steel, British Ports, Ledwood for the manufacturing side, and Port of Milford Haven as well. So one of the other advantages of this design, it's got lots of similar components in it, so it makes the assembly a little bit easier. So you've just multiple of the same part. Okay. So I'm going to be talking about the design. Obviously, we want to optimize the design, so we need to go through the process. So this is maybe targeted a little bit more for some of the academics here, what we're doing here. So first of all, we need to work out what the loads are on these structures. So we do a hydrodynamics model, we use Orcaflex for that. Those loads need to be then transferred to a structural model, so then we can calculate what the load cycles are and the fatigue life. So these structures are going to be dominated by fatigue loading, and fatigue life is going to be our dominant factor there. And there's a code for offshore structures that we follow for that. So within the project, Swansea University's aim was to change the workflow. So I'll suggest an alternative workflow we can use. So using the ANSYS environment, we can do the hydrodynamics in ANSYS Aqua. And then with the same environment, transfer the loads to structural analysis, and then we'd also do fatigue calculations as well. So accumulation of damage for the wave cycles. And this is just an example of the workflow. So I think some of the academics here will have used Workbench. So here we can have, within the same workflow, we have initial CAD model. Then we do some different load cases, and I'll talk about this. So this is different wave conditions. Obviously, offshore environment, you're going to have lots of different, the sea conditions are never the same 2 days in a row, so we've got to have lots of different load cycles, wave conditions. Transfer those, then we're going to calculate the stress ranges for those load cycles, and then we can calculate fatigue lives. So this is basically for 6 different sea states. So the advantage of bringing it all into one workflow is that we can help with the optimization. Change, for example, the CAD model at the beginning, and we can bring it all the way through and calculate fatigue life in one. All right, there's lots of challenges to doing this. For For those of you who aren't familiar with offshore structures, obviously you've got to consider the waves, regular versus irregular waves. You've got all the hydrodynamic forces on a structure. You've got to transfer those loads from a hydrodynamic model to a structural model to calculate your stresses. Another challenge in this project is just getting a suitable CAD model to do the analysis in the first place. Different constraints and contacts. You've got contact between parts, whether they're welded or however they're attached. Constraints such as it's a floating structure, it's free to move, so you need to have a model constrained somehow. So it's constraint methods. Use a 3-2-1 method. I can talk a little bit more about load cases in a moment. Obviously, like I said, the sea is different all the time, so we can have lots of different wave conditions. Irregular cycles, so load cycle counting for our fatigue calcs is a challenge. And that leads us on to fatigue life calcs. Okay. So this isn't actually for the Celtic Sea, this is an example of wave data in an ocean environment. So what we've got here on the top, we've got a wave period here, basically the time between the waves, and the wave height. So each of these points on this table is essentially a load case. So it's a certain wave height and a certain wave period. So we do a hydrodynamic model to get our stresses out for each of these. But then this is only a significant wave height and a peak period. Actually, within each of these points, there's a range of wave conditions. So you can see we can't realistically run every single point in this because each of these models can take hours to run by the time we've gone through for the hydrodynamic response and through to the structural response. So we need some way of sampling this data to get a representation so we can get an accurate life for a structure without having to run every single possible wave state. Obviously within this as well, we've got wave height and period, but also the angle of the wave is going to affect. So you may have a range of wave angles as well. So you've got a couple of ways we can sort of cluster the data. We can do just some non-physics based, so just here we've got like a k-means clustering process. So we've taken whole spectrum of wave data using a k-means algorithm to just separate it up into different clusters. So we then take the mean of each of these clusters, and then we can run points here. So each of these would be 12 runs to represent all that data. We can do that based on height, or height squared we've got here, because wave power is dependent on height squared, significant wave height squared. So that's one possible way we've got to do this. Another way, take some points, find out really what's going on, sort of more of a sampling based on understanding how wave height affects it. So we could do it almost like a response surface way through all the data, so we can sample all our different wave states that way. So that's the challenge of looking at wave data. For those of you who do, I was going to say normal engineering, but not offshore engineering. Your load cases are nicely defined normally. You'll have a frequency and a stress range. Here we've got all sorts of frequencies and all sorts of stress ranges. We have a code to work from. So when we do our calcs, there's all sorts. I'll go into a bit of detail here. So things like SN curves for our fatigue life for steel. This is steel in salt water with cathodic protection, and we've got within the code how to account for stress concentration factors, how to account for welds, how to account for mean stress effects. So we have SN curves we can work from, but the challenge now is how we count our cycles. So the SN curves will give us a life for a given stress range. But we've got wave conditions, and waves are irregular, so we don't have a nice cycle to count. So we take our hydrodynamic response, we then work out our static structural stresses, and for each point we'll have a nice cycle, but it's not going to be regular. We've got a nice irregular structure there. So we do some what we call rain flow counting, so we can count our cycles that way. But each cycle is going to have a different stress range, so when it makes fatigue life calculations a little bit challenging. And what you end up is something more like this. So this is a little plot here. So for each period of time we run this model for, we get a whole range of different stresses, or stress ranges, and mean stresses. So we've got these are all different types of cycles, and this is how many we get in a period. So then we use that. We can evaluate our fatigue lives for these points and then work out our damage. And then we sum our damage together, you know, with a minus rule. So yeah, lots of challenges to evaluating offshore structures. So hopefully that gives you a bit of a guide of what we're looking at. So yeah, I hope I'm kept to time there. So a bit of summary, yes, there's lots of challenges to modelling an offshore environment. We've done some work and we can get ANSYS Aqua to produce similar results to Orcaflex, which is an industrial standard. And there's, yeah, other work I present is ongoing at the moment. Anyone any questions? Yes, Paul.
Can I ask it might be a very beginner's question.
Yep.
So the idea of the turbine is that also takes energy from the wind. Is that insignificant compared to the energy in the waves and the period of the waves? Or do you have to think about if it's turning a lot when you're doing stuff?
No, there is a drag on it. So obviously we're not, but it's apart from that, it's considered, it doesn't go into the fatigue calc. So the inertia of it's there in the structure moving in the sea, but that's it.
On that fatigue plot, I don't know if I was interpreting it right the way to get that. Are you alternating stress dominated, so range dominated, or waveform dominated compared to mean stress? It just looks very red at one end of the alternating.
So with this plot,
So there. Or is it just that it's run for more cycles? I don't know if there's damage criteria.
you just got a whole range of, so some cycles have a mean stress effect, but it's mainly an alternating cycle.
Yeah.
But yeah, some of the cycles will, there's a whole range, some of them will have a mean stress effect, some of them won't.
You're alternating, you're very to the left on that plot, sort of to the left.
To the left.
That's where all your red exists.
Yeah. This is, the higher cycles. But each of these are still cycles within, basically what I'm trying to say, there's a mixture of cycles in there, so you've got to count for all of them.
Thank you very much.
Okay.
Okay, so we've gone from one very technical thing to now a broad overview. Dawn, if you want to come up and talk to us. Dawn and Larry, who've organised today, so thanks to them for doing all the organisation and the logistics, have been talking to a number of companies locally, and Dawn is going to summarise what they've been up to. So you need to read that.
I thought he was going to say we've moved from one very technical thing to one not very technical thing, but we'll ignore that implication. So we've been working for the last 15 months on this project called NPT-FLOWRD. Michael's leading it, and Larry and I are the researchers on the project. And basically what we have tried to do is engage with companies in Neath, Talbot to see opportunities in the supply chain for floating wind, for the floating wind sector. So this is the sort of remit of the funding that we had. We had a year's worth of money coming down from the government through Neath, Talbot, through the Levelling Up funds. And what we were offering to companies is technical feasibility studies at no cost to the company, where we would say, okay, we can do some work for you between about a month or 6 months of work, looking to see where there are opportunities, particularly relating to your sector. Neath Talbot business unit were dealing with the metal bashers, and we were looking at the sort of second and third tier companies who would be able to engage in sort of ancillary equipment and other areas relating to the sector. So what were we actually doing? Hunting around really and drawing together information from all sorts of sources. So there's a lot of stuff out there, but mostly small businesses haven't got time to delve around in what's available. So Michael's mentioned the Crown Estates. We had opportunity to speak to CADU. There's the Offshore Renewables Catapult, and people are publishing reports. You've seen this table earlier, publishing reports about detailed requirements that are needed. And also some of the existing data that comes from wind farms that are under development, in this case, Dogger Bank. And then, of course, we're involved in academics, so we're looking at published literature. But this was all about searching websites and drawing that information together in a way that would be easily accessible for the companies. So we worked with 11 companies. I'm going to try and give you, I was thinking, oh, I'll only talk about the odd one or two. And then I'm like, oh, they're all so different. I want to tell you what we've been up to. So I've sort of grouped them. Here's a group of 3 companies who are particularly interested in who were the developers who are likely to be working in this area. So we've got 9 training who do training, but they do apprenticeship sort of work, they do CAD, they do management training. So very interested to see what opportunities may be there. Insight Workplace Health, health and safety training, but they had a particular requirement to look at what could they do to ensure a system that would prevent counterfeiting of certificates. People can turn up with a bit of paper and say, I've done this health and safety qualification, but they've downloaded it from the internet. So as part of their feasibility study, we could give them options as to what might be possible for that. And MME were interested, they produce flood and blast defences, so very experienced in metalworking and large, quite large, relatively large scale. And so opportunities to work with developers in things like secondary steelwork, but also they've got experience in corrosion protection. Another group connected with the developments for the floating offshore wind, of course, are the developments of the ports. ABP has published documentation showing a proposed phased delivery of improvements to the port at Port Talbot. And we're aware already that tender went out for a £50 million contract at the end of last year, looking at changing groundwork in that area. So they're starting those developments. And the belief is that Port Talbot will be used for the assembly of floating wind turbines. That's the hope. They also, as part of their, these phases of development, have moves to have a hydrogen centre and creation in that area. And so some of the companies that we were working with were very interested and would be impacted by those port developments. ALC, we've worked with them before. They produce lighting columns, but they also have a product that monitors condition monitoring for tall structures. And so the thought was there may be opportunities for them, particularly in the port developments. We've got Davis Cranes, by their name, they do cranes. We're aware already that there's a large company called Saracens who have got a memorandum of understanding with ABP for Port Talbot. So it was looking for, okay, what might be the opportunities for a smaller crane company and how could they work together with others. Also, and I thought this was particularly interesting. In terms of ports, the belief is, although we've got Port Talbot and Swansea down the road, that there won't be enough facility just in using those ports. And so we worked with Neath Port Authority to look at whether there's a small port on the River Neath. It's disused now, it's been disused since the 1960s. It's known as the Britain Ferry Dock or Brunel Dock because the lock gates there were designed by Isambard Kingdom Brunel. If you're driving from the M4 coming towards Swansea and you look down, you can see it. And so we did some work looking at whether there were opportunities that could be developed for instance, crew transfer vessels. But because it's got that link with Isambard Kingdom Brunel, it's got some listed building status and scheduled monument status. So their technical feasibility study also included conversations with CADU and where the restrictions and opportunities might lie in that. Another company interested in the same area, this Camplas technology, they are a Bridgend-based company, but they have land located in this area at the moment. And their feasibility study was not only about how they might use, they make glass fibre storage tanks at the moment, but how they might use glass fibre in floating wind turbines, and they had an interest in how towers have been built out of glass fibre, but also looking at hydrogen storage. And what is interesting, just really as an aside here, many of you will have heard of the Celtic Freeport, which enables the ports of Milford Haven and Port Talbot to have some tax and import exemptions. This area here, where Camplas has their location, that has also been designated within that area for the Celtic Freeport. So very interesting to see how those things are moving along. Lastly, these four companies, basically their focus was related to the turbines themselves. Talk to me later, I'll happily talk to you about toilets in turbines. GenQuip produce welfare units, the sort of thing you'll see on building sites with toilets, showers, canteens, and so their technical feasibility study looked at how they might be able to use their experience for installations of toilets in towers, which we have seen retrospectively done in some locations. The case study for Hexagon was slightly different in terms of we were able to use other resources in the university, in the Welsh Centre for Coating and Printing, and they were able to look at the feasibility of some of their a new corrosion inhibitor and whether there was opportunity there. ComSpec, I'll just quickly, I think they're a fine example of how we could do for them what they couldn't do for themselves. They're a sole trader, and the technical feasibility study was looking at what might be suitable signals that could be used between wind turbines on the wind farm so that data could be collected there and then sent back to shore. And so, you know, here was work that we could do that generally they wouldn't have had time for. And then lastly, I'm sure I'm heading towards the end of my time, TWI, very interested in who the developers were to see who they could work with, but also interested in remote systems for inspection, whether that was robots underwater, looking at cable inspections, but also the sort of blade crawling inspections. And in fact, we've had discussions with them more recently where they're looking for funding so they can work with local companies and see how they can move that along and test and facilitate what is available. So what have we accomplished? A quick summary. We've done 11 feasibility study reports. We held an event at the Towers Hotel to engage with local companies. We also brought in some students from Neath, Talbot, and they were introduced to the sort of things that we're doing and other connected projects within the university. We've reached more than 100 people, and we've also helped businesses to be able to engage in R&D and to move forward in innovation. So I think considering this has only been a, well, now sort of 15-month project, it does feel like we certainly feel like there's been some interesting work, and hopefully this has been of help to local companies in Neath, Talbot. So if anybody's got any questions, Larry will be happy to answer them.
Thanks very much. Great. Okay. Dawn, thank you. That's given you, hope, a really good overview of some of the activities which we've been doing so far. One project in detail, and then this broad set of feasibility studies. And that shows us a real opportunity for future work and future things we're going to do. And one of the goals of this afternoon is to try and think about what we can do next. So Diogo from Catapult is going to tell us a little bit about some of the R&D needs and requirements that the sector is thinking about at the moment. If those of you that don't know, are you going to introduce what Catapult is?
Yes.
Okay, I will leave Diogo to explain what Catapult is and what they do.
Do it. I can skip it.
You need to clip that on, and I'll sort your talk.
So you're okay? 4.
That one.
Oh yeah, that's one. Perfect. Is he on? Ah, okay. Lovely. Hi everyone. I'm Diego Miguez. I work for the Offshore Renewable Energy Catapult. I'm going to talk about industrial innovation and R&D requirements for the Celtic Sea. Try not to repeat what the people already said before, but yeah, just introduction to the company. As I said, we're the Offshore Renewable Energy Catapult. We're the UK's leading technology, innovation and research centre for offshore renewables. Our main mission is to accelerate the creation and growth of UK companies in the offshore renewable sector. We've got unique facilities. We've got we've got headquarters in Glasgow and 8 sites around Aberdeen, Levenmouth, Blyth, the Humber, Lowesoft, Anglesey, Hale, and I'm based in Pembroke Dock in the Wales office. We've got, we've got unique facilities, especially most of our engineering is done in Blyth. We've got the blade and turbine testing facilities. We bring together, we act as a bridge between innovators, industry and academia, and with the main goal of reducing cost and risks for renewable technologies, increasing and growing the UK economic value and enabling the transition to a low carbon economy. So Celtic Sea opportunity, not to say what everyone said already again, but basically, the Celtic Sea has got ideal conditions for floating offshore wind. It's very deep site, which means some of the fixed turbines are not viable or that viable anymore. So it's a great opportunity for floating offshore wind. We got this year the leasing round for 4 gigabytes in floating offshore wind to be deployed by 2035. Further 20 gigawatts are planned for 2045. And this got the potential of the Celtic Sea to become one of the largest areas of floating offshore wind in the world, actually. Floating offshore wind, why? I just mentioned that the turbines are going further offshore, which means and implies deeper waters. There's still a trade-off to be decided. There's a lot of discussions about what is feasible for fixed or when floating is more viable. but we all agree there is a certain depth in which air fix is not viable anymore, so we have to commit to floating. There is a lot of lessons learned from oil and gas industry for using platforms. They've been using it for years and years, but have to bear in mind we need the floating offshore wind to be cheaper, more efficient and reliable and manufacturable. So not all the lessons from oil and gas are applicable here. One example is, for example, the moorings. They used to over-dimension a lot of the moorings. They use chains that are very heavy and produce a lot of noise. So that would affect marine line, for example. So you have to move away from some of the lessons learned from oil and gas and apply them particularly for the floating offshore wind. So yeah, as I mentioned, we got the potential of delivering up to 50 gigawatts in the Celtic Sea. And as we said, the first turbines that are going to be installed in the Celtic Sea would potentially be very different to the last. So the last 100 megawatts, it will be completely different to the first. So instead of being just a big number of turbines, it would be just the single massive wind turbine, or it would be a multi-rotor system, which means there is a lot of opportunities and scope in terms of innovation and research and development for this particular case. So we're going to mention 4 main areas. The first of them is for the main areas of focus or challenges. The first one is dynamic cables. So for fixed offshore wind, it's already a massive issue. So the cable failures cause 80% of the insurance claims. So which means for all the viability studies, the financials for getting offshore wind developed, it will be even worse because it's much more dynamic. There's much more stress, much more fatigue. So and it's a very unknown field at the moment with floating platforms. So there is a need of a lot of innovation and in elements like bend stiffness or new cable materials, further studies about the fatigue life. And for these, it is important to have to pay a lot of attention into condition monitoring, so to be able to detect early before failure, so detect and act upon it. So this is an important challenge overall for the offshore wind. Another example is the repair and replacement of these cables. So an option would be to have lengths that could be substituted easily. So when it's a part of the cables that fails, make it much easier to act upon it rather than spending hours and hours of time just locating it. Second challenge that we'll talk about is the moorings. I mentioned briefly before about the oil and gas. But yeah, basically, if we rely on what the oil and gas learnings and their approaches, there's not enough chain manufacturing in the world to be able to supply for these big projects from the Celtic Sea. So we need to move away from some of those. There is the potential materials such as synthetic ropes. There is designs that imply they call intelligent mooring system that can take, because the peak loads are the biggest issue with for the life cycle of the moorings. So we need to provide systems that are able to absorb that kind of impacts. And not only that, it's also the noise that these farms will generate in the area, so for the marine mammals and marine life. So I have to bear in mind, we have to take those into account when designing the moorings for the offshore wind, floating offshore wind. And basically that. So moving on to the third challenge. Am I too early? Ah, fine. So it's operations and maintenance. So basically, so fixed wind relies on crew and component transfer from floating vessels to fixed platforms. Now they're not jumping from a mobile boat to a fixed platform, going to a mobile and floating boat to a floating platform. So it adds a lot of complexity in those operations. So, and it's always considered a big risk. So the plans is to move away, not completely eliminate because it would be impossible, but to minimize the number of and duration of operations offshore. So we basically need to remove the human factor if possible. So there's a lot of innovations about survey drones, autonomous underwater vehicles, but have to bear in mind as well of all the limitations. For example, for the drones, the biggest issue with them is the wind they can take to operate properly. And we're talking about offshore wind, so it has to be windy to be viable. So there's a lot of limitations we have to bear in mind when designing these systems. But that is basically what we're talking about. Another important bit is the communications. We're talking about, there's some projects already looking at using 5G satellite communications to provide the data, but we still have the big issue, I'm about to comment on it, which is if we've got seabed or underwater systems, there's a lack of bandwidth. So we struggle to have enough data transferred to those 4G, 5G satellite points. That's one of the bottlenecks there. So the last of the challenges is the environmental monitoring. So yeah, it's a subject big enough to have an entire event around it. But yeah, there is a lot of new technologies that we have to develop for this, for offshore, floating offshore wind. So we need to, a lot of the current approaches are point measurements that might not provide enough information of the whole area. So we're trying to move into regional approaches rather than point or precise tiny areas, doing like a holistic approach about it. We also need long-term monitoring as well, not just for 1 month or a couple of months a year. There's a lot of variability into the ocean we have to take into account. So we're moving into systems able to be deployed long-term and account for not only seasonality, but also what happens through the years. And as well, is not only for the planning and pre-deployment, it's also installation and post-installation times. So we need to have robust systems that are able to collect for long term. So that's pretty much the 4 key challenges that we see that are going to be in the Celtic Sea in the future. Just to mention some of the projects that we're involved with along these lines, we've got the Rescue Project, which stands for Regulations to Ensure Sustainability, Circular Use and End of Life for Wind. It's been it's a comprehensive and robust end of life materials handling network. It's being identified already more than over 150 policies and regulations that could be applied to UK wind turbine end of use management. So we're talking about not only the installation and the operation, but we have to think about the end of life of these farms already now, because in order to be able to decommission properly, you have to think on the design phase already. So yeah, it's an ongoing project we've got on the catapult that's looking at policies and regulations for the end of life of these farms. And another one that I'm particularly involved with, which is the Subsea Soundscapes project, is OWEC funded by the Crown Estate. We're doing it together, the catapult, with Celtic Sea Power and University of Exeter. Basically, we're doing a regional approach so we're deploying and taking long-term measurements for at least 2 years in 21 stations around the relevant areas for development of offshore wind in the Celtic Sea. We're combining, the existing, I can describe around, but you can see the red dots are out of those 21 places, the red dots are the Welsh waters, green ones is English waters, and the yellow ones are data provided by the Crown Estate already. So this is a big grid that's going to be providing, collecting data for 2 years at least. And the data is going to be open source and freely available for everyone to use. And there's a lot of secondary objectives with it. So if you've got any plans or you work along those lines to add value to the project, please contact us and give us a shout, because we're really keen on what other projects could benefit from this. But yeah, that's basically what we're working on. So it's not only collecting acoustic data for long term, but we're also doing eDNA sampling for any of the maintenance operations we're doing, and CTD sampling as well. So that's the end of my presentation. Happy to take any questions.
Okay, we have time for a couple of questions for Diego. So,
sorry, it's not a question, but maybe a suggestion.
Sure.
For the benefit of everybody. But there's a project that we haven't talked about today, which is in PTZ, Pembrokeshire Demonstration Zone. And I'm the project developer for that from Dolphin Hydrogen. So that's going to be an offshore hydrogen production from floating wind. I think it'd be nice if we brought that into the concept. And the reason for bringing it up is it's a project we're doing with some of your colleagues.
Yeah, yeah.
And funded by Innovate UK. So it'll be a 135 megawatt project. So it's a big ambitious project, but it also has some different things for me, like of course no electrical cable, but it does have a pipeline back to shore. So it'd be just nice if we brought that into some of the things, because I think there's some really good opportunities for people to start thinking about.
Yeah, definitely. But yeah, combining the, well, you could use existing pipelines, but there's also, yeah, the hydrogen is...
We'll see what we're going to do now.
Coming back to a couple of the challenges that you talked about, particularly around the dynamic cables and the moorings. As I was saying in my talk, one of the kind of characteristics we've got is that we don't know exactly what technologies are going in, and we don't know exactly who's going to be making the cables and the moorings. Do you or does the Catapult have an idea of what kind of partners that a university would work with to do meaningful research on the dynamic cables and on the moorings in order to actually have an impact on the
Yeah, well, I could put you in touch with the people in the Catapult dealing with the dynamic cables, but we've got a team that is working on it, and we've got a couple of collaboration projects ongoing, but yeah, happy to put you in contact with them. Yeah.
Okay. One more? We got any more? Yes.
What is the lifetime of one of these floating turbines? What do you anticipate?
Oh, I think currently they're working around, they're moving away from the 15 years to the 25 to 30, but it depends. Yeah, these newest technologies I'm not too sure because it's changing everything, it's changing very fast. But yeah, I think the idea is to from the design to make it last much longer because of all the implications. It's not only, well, at the end of the time it goes to financial implications, but we want, to reduce maintenance, to reduce replacements, to reduce everything. So the sector is moving towards a longer periods for the turbines.
Okay, thank you very much.
Thank you.
Need the mic.
Oh, sorry.
Okay. Right, I'm going to explain what we're going to do next, and then the people online are going to go into a Teams meeting, hopefully, and have the same conversation, which Larry's going to look after. So what I want you to do next in the room is pick up a Post-it note and either write on it something you need to happen. I'm looking at our industrial friends in the room. If you've got an industrial need or a question, or you feel that one of the industrial projects, the feasibility studies has really sparked an interest, write that down and say, this is something that we need as an industry. And those of you who are academics in the room, I'd like you to write on your Post-it note things you can offer against one of the challenges you've seen, either something Diego has said, something that came out of the feasibility studies, just to say, I think I can offer this skill or this expertise or this piece of equipment into that question. And then have that conversation with people on tables around you. Please move if you're on your own a little bit. And then we're going to carry this on until 2:40 when Alpa is going to start talking about our wind tunnel. So those of you who are online, if you would like to leave us at this point and join our Zoom call. We also have, if you'd like to re-top up your coffee over the next half an hour, but you have to write one Post-it note before you're allowed coffee. And my second rule is don't queue. So if there's a big throng of people, keep chatting on your table and go up a bit later on. Okay? If that's all okay, if we're all clear about that, please make a start. Flow is quite important. Alpa's going to talk about our wind tunnel and some of the projects he's done there, and then Alison's going to follow that. So Alpa, over to you.
Thank you very much. So one of the speakers before said her talk is not technical. Mine will be even less. It's completely, there's nothing technical. It's about wind tunnels and what I do, and it will be quite tangent to the wind turbines and offshore wind turbines. I hope you will enjoy it. So I just put this here in like an icebreaker. So what we are doing is under Climate Action Research Institute, and there are like 5-6 different research aspects around it. And what we do in the wind tunnels we have here at Swansea, I put like 4 or 5 different pictures there. 3 of them I directly work on. Some of them we don't do yet, but we can do those things. So at the top, you see FLI 0. So most of the research activities I'm doing is directly about net zero activities in aviation. We are doing research around wind turbines. It is mostly indeed still related to Ian, but I would say we are doing the wind tunnel. So we can do things about urban planning as well. We haven't done it yet, but I am planning to do things about this. We are doing lots of things about biomimicry and designing new kind of flow control techniques. In overall, what I do, I'm an experimental aerodynamicist, and I work on general flow control techniques, which I can apply to the aircraft, to the wind turbines. It doesn't matter to me in terms of what the application is. I generally work on the flow control technique itself. Okay, so what I will show you, just a few examples about what we are doing here in the wind tunnel facilities here at Swansea. And all this work that I'm going to show you is, of course, coming from my PhD students. And we have 2 wind tunnels here at Swansea. I'm not sure if you know what a wind tunnel is. Wind tunnel is just a huge pipe system where you create a controlled airflow. So instead of making a design and manufacturing in full scale and putting in place to test, you just make a small scale of it, and you just mount it in a controlled environment, and you try to understand how it will behave in the actual case. We have 2 wind tunnels. One of them is on the left-hand side is on Bay Campus. That's the one that I'm managing. It is a low-speed wind tunnel, and you can see the test section. It's not visible very well, but if I just change this to laser. So this is our test section. You see a small human here. So the test section is around 2.5 meters to 1.5 meters to 1 meter. And we have another wind tunnel facility, which is on the Singleton campus, and that is specifically built for avian flight that I'm going to show you as an example. That wind tunnel facility, when I say avian flight, is for we fly birds inside it, and that facility can tilt up to 8 degrees because we can't ask birds to have an angle of attack. So we just tilt the whole tunnel, and we do experiments to have some gliding performance. So these are the facilities we have here in Swansea, and I will just talk about what we are doing. So all of my work with my 4 students, we work about gusts and turbulence interaction. So I started to work on this topic for the last 2-3 years now. All the experiments, etc., we were doing before, it's always in smooth flow conditions, but real life isn't like that. If you have a, let's say, wind turbine, it always is getting exposed to gusts from sides, or let's say different levels of turbulence. Or if it's an aircraft, again, it's the same. If it's a drone, it's the same. So with my 4 students' projects, I'm just trying to develop a knowledge base about how gust and turbulence interaction plays effect in all these kind of applications. The first application is urban air mobility vehicles. This is, we are doing this with Embraer, world's 3rd largest aircraft manufacturer. And this is about how, I don't know if you heard about this flying taxi concept. So this is all over the place now, Vertical, Joby, lots of aviation companies are trying to build one. So those ones are, again, for net zero, the propellers are, or rotors are driven with electric batteries, and you can have multiple rotors or propellers, and every company has a different layout. So we don't know how those rotors really interact with each other. Their wakes hit to each other, and they just change their, each other's performance. And the worst case, We don't know how they will also react under gust and turbulence when they take off or land. If you want to land it here, there's a huge building there. It will have a wake. There will be a gust behind it. So we don't know what's happening. None of the companies know, so they are spending so much money on these research activities. And this is what we are doing. You are seeing two rigs here. One of them is just about rotor-rotor interaction, and there will be 4 of them in the end. And we will be subjecting these things to different gusts. When I say gust, a controlled, like a sine wave, or a homogeneous turbulence, different levels of turbulence. And we will see how the propeller performances change. We will also install a wing and see what's happening for the overall performance of the aircraft. This is one thing. And we started to do experiments. We have the rig. This is one of the results that we just collected like 2 days ago. So you see, for example, the thrust generated by the propeller when it's got hit by a gust, a discrete small gust. You see how the thrust surges and then it goes down again. And we need to quantify all these things to understand how these structures will work. So we do lots of biomimicry. As I said, I work on flow of control, and I aim to develop flow of control techniques based on bioinspiration. So in our other internal facility, we have been doing experiments with pigeons. Now what you are seeing is a pigeon, again, flying under gust. You don't see it, but there's a gust generator here. It sends discrete or continuous gusts. That pigeon have lots of markers on it, you can see. And then we are just getting the whole kinematics of the bird. There are 2 things that we can do, just from scientific point of view, how these birds react to gusts and turbulence. Professor Shepherd from Biosciences, she has been already working on pigeons in their natural habitat. Now we are doing experiments in the wind tunnels, and we are trying to understand how these match. But what my aim is, again, to learn from here and try to apply, try to find out a flow of control technique to stabilize drones or other small MAVs that will be in use. Because if a pigeon can stabilize itself in, let's say, one flapping cycle, can we do it for a MAV or UAV? And from here, what we do is simply we are getting all these markers locations, and then we can define anything we want on a pigeon, how much it rolls, how much it does a pitch, how the wing area changes, etc. And then you can do higher order analysis. You can calculate accelerations, how the wing accelerated or not. And then we will try to, this is also new, we are trying to understand if we can figure out a flow of control technique from here. And the last thing is about, more related to you guys, it's about wind turbines and wind turbine blades. Most of the projects were led by Ian Masters before. This is one of my students' project. He was doing it from his 3rd year, and then he's still continuing to do this. This is about an active control for a wind turbine blade. And luckily, one of the companies Ian was working before, Anakata, has funded this project plus their own projects. I will talk about it. Well, I have limited time, so I will quickly go through this. So, for example, this one was a leading edge active control. There was a rotating blade here. So we are doing experiments on it with different leading edges. This is for a wind turbine blade, and you can see how the stall characteristics change. So this is the beige one is a standard blade, but then the rest is with an active control, and you see the stall doesn't occur until 40, 50 degrees indeed. And there are other studies that have been done in the wind tunnel facility. There was a project with Vestas. They have done a project about flatback airfoils, which is again used in wind turbine blades. We are doing some other small projects. One of my colleague, he had a project. Indeed, it's supported by ORE as well. And we are trying to figure out an experiment about how to, so his project is about observing health monitoring for wind turbine blades with a drone, but to do that, you should keep your drone in a fixed position or in the same position with the blade. So we are trying to do a scaled experiment for this, which is not easy. We are thinking about it. Yeah, that's it. So this is just a general thing that we can do with wind turbines, and we are all doing these things with my students, which are great. So if you have any questions, I'm here to answer.
Okay, time for one question, if we want to. Right, okay, thank you. Alison. Oh,
Right. Sure, put in that.
Okay, my colleague Dr. Alison Williams is leading our work on computational fluid dynamics of turbines, so I'm going to let her talk about that. Thank you.
Okay, thank you. Hello everyone. What I'm going to talk to you about today is the work we've been doing on building a computational model for arrays of turbines. So this work has been led by myself and Ian, and has been supported, it's been going on for quite a few years, so it's been supported by a team of postdocs, so I'm just acknowledging them here. So we have spent quite a long time building this turbine array CFD tool. Now here CFD means computational fluid dynamics, not the CFD that you saw earlier on in earlier presentations. And our motivation was to be able to develop an efficient open source CFD tool that would predict horizontal axis turbine performance. We wanted to build this for, well, we were originally looking for tidal stream turbine devices, but then we've subsequently applied it to wind turbines as well. Now, we know that the performance of a turbine is dependent upon the characteristics of the turbine, so we knew that we needed to be able to implement that within our model. But we also wanted to be able to represent the environmental characteristics, so things like flow behavior, having realistic flows, and also embedding sort of the surrounding geometry related to maybe the seabed bathymetry if we're dealing with tidal turbines, or if we're dealing with onshore wind turbines, you know, the landform that they're located on. So we needed to be able to build that into our model as well. And we were thinking well ahead and thinking we want to be able to get this model working efficiently for arrays of turbines. You know, so not just for one turbine, we want it to be able to look at arrays of turbines so that we can optimize the performance of those. So we spent a lot of time and we've ended up developing a model which we've called Generalized Actuated Disk Computational Fluid Dynamics. It's a bit of a mouthful. We've shortened it to GAD-CFD. And this is an open source piece of software that we have implemented in OpenFOAM. The idea is that we represent the characteristics of the turbine. We time average the characteristics of the turbine over a disk, where the disk has the same diameter as the turbine itself. And this avoids us having to represent the physical features of the geometry of the turbine blades within our model. That makes the model more efficient because we don't need to mesh around the blades. So that means we can have a simpler mesh that reduces computation time. And we also don't need to run it as a transient process. We're time averaging the behavior, so we're looking over quite large time scales, so we can run it as a steady state problem, and we get an answer out a little more quickly than dealing with the complexity of transient analyses. So this tool has been, as I said, implemented in OpenFOAM and is now available on our Swansea site, the GitHub repository that's hosted here. So the software can be downloaded from there. There's also training materials and some benchmark test cases. And the work was all put together as part of, well, the release of the tool was all put together as part of the Celtic Sea project, which was a Interreg Ireland Wales funded project. So in terms of data inputs and outputs, what the model needs to know is it needs some information about the rotor. We are trying to represent the rotor as effectively as possible, so we need to know how the blade characteristics vary along the radius. We need to know some information about the lift and drag for the particular blade, and we need to know what tip speed ratio it's operating at, etc. We can also, within the model, embed information about the support structure. So we can take the geometry for the support structure and embed that within the model. And we need to know something about where this turbine is operating, or where these turbines are operating. So we need to know about velocities, turbulence intensities, bathymetry if we're dealing with tidal turbines. If we're just doing tank testing, I say just, if we're doing tank testing, we can import the dimensions related to that, wind tunnel testing, etc. Those are the inputs. And then for the outputs, the model will predict the output for each turbine that is being modelled. It will also output information about power, thrust and torque coefficients, and it will give us some information about the wake characteristics. So we'll be able to see for a given set of operating parameters how quickly we get wake recovery. And if we're dealing with arrays of turbines, we can see how those wakes are interacting with turbines that are downstream of them. So as I said, it was originally designed for tidal stream turbines, and we did a lot of work testing and validating the model for that, looking at single devices and arrays of devices. And then we've subsequently applied it to wind turbines and done some validation on that. So we're fairly confident that the model is behaving as it should. It does good predictions of power. So we can see if we're looking at power or CP, your power coefficients and thrust coefficients, we know it's behaving well. We've also looked at the wake recovery and been able to get some confidence that the model is accurately predicting wake recovery for these models. So I said we moved on to looking at wind turbines. So I've got an example here of an onshore wind turbine array. So this is an array of 16 turbines sitting on a hillside. So we've got the model of the hillside built in, or the topology of the hillside built into the model. The turbines are distributed as shown here. The wind we've got a fixed wind speed. The wind is coming in this direction, normal to the way that the turbines are orientated in this model. All the turbines are orientated in the same way, and the wind is directed normal to them. That's just the way we've chosen to implement it. You could have them orientated at different angles. And when we've run that through the model then, we can get a range of outputs. So over here on the graph, we've got some representation of the power that's produced by the individual turbines. This is a normalized power graph, so they're normalized, they're relative to the turbine that's at the front. But you can see we're getting quite a variation in the power that's being predicted, depending upon where those turbines are located. In particular, we notice that the turbines that are located in this region, they are the ones that seem to be behaving the best. They are producing the most power. Whereas when we move a bit further downstream, we seem to get a drop-off in the amount of power that's being predicted. And the reason for that is, if you look over here, it's because those turbines are being affected by the wakes of the upstream turbines. So particularly if we look at 10, 11 and 13, that's this turbine, that turbine and that turbine, they are being really affected by the wake. It hasn't fully recovered, and so understandably they're getting lower power. Even more quite interestingly, I think, there's this turbine here, which is turbine 12. That seems to really benefit for being positioned where it is. And that's because it's benefiting from the bypass flow that's coming off the turbines that are in front of it, and the flow's accelerating between them. And so this turbine here is getting some benefit from where it's actually positioned. And by moving the positions of those turbines, we can then help to understand how that array is behaving and position them so that we get more optimum performance. Okay. So, I haven't shown you any examples about applying this to floating offshore wind because we haven't tried it yet. But we have some confidence that we know that it's behaving well for tidal turbines and onshore wind turbines. So we are fairly confident that we could apply this method to floating offshore wind because we know it's got the ability to model turbines and their supporting structure over a range of flow characteristics. And so we think the tool could be useful to maybe site developers, device developers, academic researchers, anybody that's got an interest in this field who might be interested in trying to arrange arrays of devices in order to get optimum output from their turbines. And that's where I'm going to finish. Any questions?
I
can get it off, you can have it.
got a very quick one for you. Are you looking for an offshore project to work on?
Yes.
Good answer.
Great, thank you. Thanks so much. Okay, so thank you all for coming. I hope that you have seen a glimpse into some of the detailed technical capability we have here at Swansea, the things we can do, some of the projects we've worked on around offshore renewables and floating wind in particular. And at this point, we've got to the end of the formal session of our agenda. So the first thing I want to do is say thank you and goodbye to the people who are online for joining us remotely. So I hope you've got something out of that, and please get in touch with the team if you have any further questions or things you want to follow up. Thank you. Right. For the people still in the room, thank you for your time. You're now free to leave. Those of you who have time to stay, we're going to start to think about whether anything that's been written down on the post-its or any of the ideas we came up with earlier could turn themselves into projects. So we've got this room for the rest of the afternoon. There's still coffee. There's still biscuits. So if you want to sit and chat for a bit longer and turn some of these ideas into project ideas, then please take the time to do that. Otherwise, thank you all for coming, and goodbye.